Hello and welcome. My name is Debbie Cavanis. I'm the Alumni Director here at the College of Environmental Science and Forestry. Welcome to our inaugural episode of Esf Connected, where we will be bringing you highlights from our faculty and staff and research that they are doing on campus. Today I'm joined by Dr. Bahram Salehi. He will be doing a presentation on North American wetland mapping and monitoring from space. So Dr. Salehi joined the college in 2018. He is an assistant professor of remote sensing engineering in the Department of Environmental Resources and Engineering. Dr. Salehi is a world-renowned scientist known for remote sensing of wetlands and is the second top author in the Web of Science in his field. He has also published nearly 50 peer-reviewed journal articles and books and chapters. Dr. Salehi's expertise in the area of optical and radar remote sensing have been a tremendous addition to the college. So Dr. Salehi, thank you very much for joining us today.
Thank you very much, Debbie. That was a generous introduction. Good afternoon, everyone, and I'm glad that I'm here today trying to share some of my experience with the work that we are doing on wetlands of remote sensing. All right, so I guess this is probably not a very, common topic to many of you. So I'm trying to basically discuss as much easy as possible, not going to the complex of what we're doing here. But so the goal here is to basically provide a wetlands inventory of North America. What I mean by wetlands inventory is a seamless wetlands inventory map of North America, including Canada, US, and Mexico. So this work has started I have started this work some 5-6 years ago when I was in Canada and I finished my PhD and joined a company called Seacor and Memorial University of Newfoundland up in Canada. So when I joined there, I've discovered that there is no really a wetlands inventory for that province at the time. And that was partly because of the harsh environment and the fact that not really all common remote sensing approaches would work for that province. So I started exploring that opportunity with some additional resources and some additional technical expertise. So we've got some support from Environment and Climate Change Canada. And I was lucky enough to build a strong team of grad students to start working on wetlands inventory of Canada. So we started working on that, and we finished last year in 2019, the first wetland inventory of Canada with high-resolution satellite imagery in 10-meter resolution. And the second generation, which basically was a higher accurate wetlands inventory of Canada with the same spatial resolution but higher accuracy in 2020. So as Debbie mentioned, I joined the ESF in 2018. Since I've moved down here, we started to extend our collaboration and the work of wetlands to the US, obviously. So, of course, US wetlands inventory is more advanced than Canada. The current status of US wetlands is much better than Canada. But still, some of the wetlands maps are old, and some of the states still does not have full wetlands inventory, such as Alaska. So building on my past experience, we started to develop partnership and collaboration with regional and national partners, such as Ducks Unlimited and U.S. Fish and Wildlife Service. Now we are working toward the wetlands inventory of the U.S. And the goal, like I mentioned, is to move toward a wetlands inventory of North America, including the three country of the subject here. So now I'm going to move to a little bit more on the concept of wetland. I am really not a wetland scientist in nature. My expertise is mostly remote sensing, engineering, and processing of satellite data. But throughout the past few years, I've really enjoyed basically helping wetland scientists and stakeholders to understand and map this valuable environment. So what is wetland at all? That might be a good question to start with. So wetland is basically a part of land that is permanently or partially covered or flooded by water. And there are some different definitions in books and literature, but the one that I really, I guess, carry the meaning is that a land that basically is covered partially or completely with water over years, permanently or seasonally, of course. It does not need to necessarily be permanently flooded. So some people say wetlands is the nature's kidney, and I really like this terminology because really it is. Wetlands is an important ecosystem. If it's not the most important ecosystem of all, it is one of the most important of ecosystem on our environment. So there are multiple functionality that is done by wetlands. Wetlands basically filter water for us. It provides sites for recreational activities. It protects us from natural hazards such as flood. Of course, it provides a great habitat for wildlife, and many more. I'm sure many of us have enjoy our outdoor activity in a wetland site, or have passed through, take a hike through a wetland and enjoy. So wetlands is important. So these are just some general, basically, benefit of wetlands. Now, why wetlands is important to be protected, and why should we care at all about wetlands? So some report says that almost 56% of North American wetlands have been lost during the past 300 years. That is a sad news, but unfortunately it's a fact. And the other sad fact is that more than 70% of this loss is happening near urban areas, which is not surprising. I mean, urban development and urban sprawl always speed up the loss of our ecosystem, and wetland is not an exception. And unfortunately, again, more than 50% of this loss is happening the last 40 years, which is, again, necessitate us to take action toward protecting this valuable ecosystem and environment. Now, so we need to take action to protect our beautiful wetlands. But how? So we need some information, some original information to build on our effort for conservation and for protecting and really helping the nature to keep this valuable environment. In order to protect our wetlands, we need to answer some of the fundamental question of where those wetlands are located. What type of wetlands are there? Because there are many different types of wetlands in the context of the country and geographical locations, which are different from, they're all valuable, but different functionality and different importance, I would say. Then we want to know if there is any change happen to a wetlands site or wetlands ecosystem, when that change happened. And also, we want to see how big is that specific wetland site. So North America is probably one of the richest continent of wetlands. I know that only Canada does own some 25% of the total world wetlands. So a lot of wetlands are distributed across North America. So in order to answer these questions, traditionally field work, ground visit, and in some cases aerial photography have been used to answer those questions and grab some information. But really talking about a continental context or a scale, ground visit is impossible. You can't walk through all North American wetlands and try to map them and take note them with your handheld GPS. Aerial photography also has a lot of limitations. First of all, it's very expensive, and it does not cover a huge area. Plus, that there are some logistics issues and basically atmospheric issues, such as in cloudy, rain, and all those that airplane cannot fly. But off top of all, covering an entire continent, such as North America, with aerial photography for the purpose of wetlands is extremely expensive and time-consuming. So really, when it comes down, the solution, probably one of the only solution is remote sensing. So remote sensing, when we are talking remote sensing, some people may say, well, aerial photography is part of remote sensing. But yes, but here in this context, remote sensing, by remote sensing, I mainly mean space technology and space imaging. Oh, well, remote sensing is helping us because it is a fast, it is a cheap, and it is a very accurate technology for this purpose especially. Again, large-scale mapping really needs a huge coverage of satellite, and for basically not for a static mapping, what we call it static mapping, which is one-time mapping, but we also want to monitor the change over years, over time. So remote sensing data is a repeatable source of information that satellite can fly over the Earth and acquire image on a frequent basis. Now, just to give you a little bit information and put it into the context, is that this work that I'm presenting here is, of course, is with the great help of my collaborator and partners, and most importantly, my grad student over the past 5 to 6 years. Some 5 students, 4 of them have been graduated successfully, all of them in Canada, but I have right now a PhD student who is working with us now, and this team is growing toward the wetland inventory of the US. And we have more than a dozen partners and project collaborators, national, international, and NGOs, academia, and industry, that I'm going to really appreciate them. And probably the least that I can do, just acknowledge them at the end of this show. And we have published nearly 30 peer-reviewed journals exclusively on wetlands. So that is why we really take care of our wetlands. And so our approach is really take a rigorous and huge science-based approach. So it's not trial and error. So we are developing methods and algorithms, publish them, and then we try to implement them and basically bring them to the real world and solving a real world problem. Now, so speaking about wetlands, there are different type of wetlands, and definition of wetlands depend really on geographical location. Apart from that general definition that I gave you earlier in my talk, when it comes to Canada, the wetlands are different than in the US, the wetlands definition. For example, in Canada, according to the Canadian Wetlands Inventory, there's 5 major types of wetlands, so-called bog, fen, shallow water, swamp, and marsh. So really the goal here in the Canadian side is to map all these 5 major types of wetlands and distinguish them. In fact, this is a really challenging task. Even, like I mentioned, I'm not a wetland scientist, but I have worked with a lot of wetland scientists and biologists and ecologists. They are all pretty much agreed that distinguish a bog from a fen, even with site visit, is challenging. And most of the time, there is an agreement between whether this is a bog or fen. Well, there is some technical, basically, definition behind them. But, at first, I was thinking that when we cannot distinguish a bog from fen just from 2-meter distance or a couple feet, how we can distinguish this from 500 kilometers above the Earth from satellite. But that's the beauty of remote sensing, actually. So we are trying to, in this work, we have tried to leverage all the opportunity that remote sensing technology has to offer to us. In other words, we are using not single source of data. We are building our method and algorithm on multi-source data that bring and pick different type of information. Specifically, my expertise is in radar remote sensing. So we basically get combine information from radar remote sensing plus optical remote sensing, and of course with ground truth information. We combine them, put it in the software, and the software is able to do the job for us. Before I move to the next slide, I want to mention that some may ask you, what is the definition of shallow water here? In the context of Canadian Wetlands Inventory, the shallow water basically refers to any water body which is 2 meters or less in depth. So of course, radar remote sensing cannot penetrate to water, but optical remote sensing, when I say optical remote sensing, you can imagine of your cell phone camera or your camera would take pictures. The difference between an optical sensor with your cell phone camera is that your cell phone probably only take an RGB red, green, blue natural color composite image, but your multispectral, but the multispectral sensor on board the satellite can acquire more than 3 bands. It can get near infrared, short infrared, thermal bands, and all those that are all complementary for distinguishing different type of objects on ground. So we combine these two type of data, radar and optical remote sensing, in order to map and first detect these wetlands, distinguish them from upland, and then distinguish them between themselves. So that is the job, and that is really the technical objective that we are looking to solve in this wetlands work. Now, so again, speaking about remote sensing, I guess I want to just briefly mention the steps that is involved in a remote sensing project when it comes to wetlands context. So first of all, of course, we need to collect input data. And as I mentioned, input data is mainly satellite data. So we have built the algorithm and methods on satellite data, which is not expensive, or better say, are freely available and publicly available to public. Because again, talking about wetlands inventory of 3 countries, 3 huge countries, or even a single state using costly satellite data doesn't make sense from engineering and from cost perspective. And I would add this to that we need to monitor this over years. We can't allocate that much money every year in order to protect or observe our wetland. And that's the big reason behind this method, that we are building this method on freely available satellite data. There are multiple satellite data that offer free service to public and to researcher, including those from NASA, Landsat. I'm sure many of you are familiar with Landsat mission. Landsat, and recently European Space Agency satellites such as Sentinel-1 and Sentinel-2. So satellite data is becoming more and more available to public, and we're taking benefit of that. In fact, NASA is planning to, and in collaboration with USGS, is planning to launch the next generation of Landsat, which is Landsat 9, maybe this year or next year. So that is another huge data set that add to the proficiency of this work. Many work like what we are doing here. Then, of course, satellite data always on its own is not enough, I would say. So you have to cross-validate what you're watching from space with the real world on the ground. So you have to go to the field and collect a few samples, very, very few samples, maybe less than 0.01% of the total area. But you need those field data that is used to train your machine learning algorithms and to validate and evaluate your result. So that is probably the most expensive part of a project like this. But we have been lucky enough that I have used the approach to partner up with many industry and NGO and organization that are generously providing us with these data sets, and in return we provide them with the technical expertise and the map as well. So you can imagine with funding from academia, allocating fund to go to the field to Alaska and all those states, it's probably impossible. But this is the beauty of collaboration with industry and basically federal and state agencies. Like I mentioned, Ducks Unlimited is generous enough to provide us with some of these data set that they have collected. U.S. Fish and Wildlife Service also, we're collaborating with them. In Canada, we work with U.S. in Nature Conservancy Canada and Ducks Unlimited Canada, Environment and Climate Change Canada, and all those. So these are the data set that they have collected, not necessarily for the purpose of our work, but they have collected for, say, for agricultural mapping or a byproduct of one of their projects. So these data sets, we have memorandum of understanding with them. We use their data sets and we provide them with a product. So that's really the part that I really enjoy working with all these great organizations. So now we've got collected satellite data, we've got ground field data. Now we have to combine and put them in software processing. This is the machine learning part. The PhD students and researchers are involved heavily in developing algorithm to process such heavy sets of data with proper algorithms. I'm not going to detail much of this machine learning algorithm. I probably have a couple, I hope, an interesting picture for you in the next couple of slides. But I am more toward, sort of sharing with you the result as we move toward the next few slides. Now, so again, this slide sort of summarizes what we are doing. So we collect satellite data. The left side of this slide shows all these different satellite data that we collect data from them. So we are not working with the satellite. We just use the data that they're taking. Then we combine with our field data that have been collected by partners. In this picture, we have grad students. Most of these people in here in this slide are my former grad student up in Canada. That sometimes we need to go to the field and collect field data, in addition to the ground truth data or field data that we are getting from partners. Then put them together, stack all these data sets, and provide a map. So the right map is the final product. That is a GIS-ready layer of data sets. So this GIS-ready data set can be transformed to any organization, municipalities, transportation companies, climate change activists, and so on, to use this layer of wetlands. For example, I will give you an example here. If a municipality want to build a site, a warehouse, or they need to know where are the wetlands are located in town. So in order to avoid building on that valuable environment. So they need a map of that wetlands. If they want to build some policy about flooding and do some action to avoid flooding, they need to know the map of wetlands. If a transportation company want to basically build a highway, if a transmission company want to build a power line, they really need to know the map of wetlands in the area to avoid as much as possible crossing those wetland sites, because there are regular and policy forced by an environmental agency that a wetland cannot be disturbed, or part of that wetland of a certain level. I don't really exactly know the exact number, but there are some rules and regulations that prevent construction and building over a wetland, and that's why wetlands need to be mapped and protected. Now, let's move to a little bit. This is probably a little technical slide. So this is basically what we have. This is the framework or the methodology or machine learning methodology that I talked. We are building on this to use our wetland map. Down the bottom, you see that Dr. Matt Yunperry, who is one of my former PhD students, he's a great scientist. He's still working with us. So the co-author of the couple papers that you can see in the link of this work. But basically, the method starts from, again, satellite data on the left side of the slide you see. These are both radar and optical satellite data. I keep saying about radar and optical because these two set of data are complement each other. For example, optical satellite data, which is Sentinel-2 in this case, grab information regarding the color, regarding the health of vegetation, regarding the floristic information of wetlands. On the other hand, radar pick information regarding the structure and the flooding status of the vegetation that are important in a wetlands. So they pick up different sorts of information, and then once we grab all this information from satellite data, we inject them to the classifier or our machine learning algorithm with heavy processing power, and the machine learning is trained using some sample data, and then ultimately it gives us the map. So in this case, we have built our algorithm using the Google Earth Engine. It is a processing platform that is, again, freely available to researchers. So we take benefit of that. This is a huge, basically, engine that offers the access to satellite data as well as high power processing. So I mean, we cannot really. It is impractical to process all a countrywide satellite data on a single computer. So we need to use basically a cloud processing technology, and in this case, we have used the Google Earth engine. Now, so I talked about the algorithm and processing behind it, and let's get into a little bit of result here. So this slide shows the number of satellites that we have processed for Canada. So Canada is a huge country in terms of the geographical area. So initially we started with some 200,000 satellite imagery. But none of all of these satellite imagery are useful or appropriate, because some of them are noisy, some of them have black spot in them just because of the malfunction of the satellite. Some of them, more importantly, are contaminated with cloud, so you cannot see beneath the cloud, especially for optical data. So after pre-processing and filtration, we reduced those number of noisy image, I would say, to some 70,000 images. So of this 70,000 image, majority were optical imagery, covering the entire country, from Ontario to Northwest Territory and so on. So coast to coast to coast for Canada. And this slide summarizes, so our method basically was not a one-time application of all satellite data. We started to basically stratify the country based on the different ecozone, based on Environment and Climate Change Canada document. So this slide basically shows the number of days that we used we spent, or the computer spent, to process such data for different areas. You can see that in total, some couple months that is used if you use one by one sequential to process such data. Of course, you can do this with multiple computer, because you're all using basically to Google Earth engine. So and the number of satellite, as I mentioned here, we in I guess summary, I can say that some 55,000 optical remote sensing Sentinel-2 data we used. Each Sentinel, to give you some context here, each single set of Sentinel-2 data is 300 by 300 square kilometers, if I'm not mistaken. So, or 280 by 280 kilometers, something along those timelines. So you can see that you can multiply that 50,000 by that area, so you can see how big. Not all these, so many of these images are overlapping to each other, but you can see that how big an area is under processing. And then on the other hand, we have Sentinel-1 with the same or similar coverage to Sentinel-2, that is radar, but we use some 15,000, I would say, I guess, close to 13,000 of radar data for Canada. Again, radar is not sensitive to clouds, so basically it can image under the cloud. So doesn't matter if it is rainy or not. Of course, if it's not rainy, the quality is better, but still can acquire image under the cloudy condition, which is, of course, you cannot take image when you're sitting in an airplane. You cannot take picture of the ground if there's cloud below you using your cell phone. But radar imagery can do that job, because they basically they have penetration power through cloud. So that's one of the beauty of using radar, especially for northern latitude, because you're facing with lack of sufficient and cloud-free imagery. Now, I discussed a lot about the technical and the processing power and all those, and here now is the final map of a huge country like Canada. So this map shows the first Canadian wetlands inventory that we generated in 2019. It has been published already. And on the right side, you can see the legend, the different type of classes that we have mapped with different color. So this is just a snapshot of the map, of course. So this is a huge layer of GIS data set. but this is just a snapshot. So as you see it, the accuracy is some 79%. The overall accuracy is not great, but it's better than what was available at the time. So you can see different classes of wetlands: bog, fen, marsh, swamp, and shallow water have been distinguished and classified. Water, so in here I want to emphasize that the water is not only shallow water, but also the deep water as well, in this color with blue, and some other classes depending on area. For example, in prairie areas, we have agricultural lands. In northern area, we have land covered with snow and so on. And some areas includes a class of urban areas. So this is sort of a general classification legend that shows in this slide. But obviously, for the GIS layer, for practical use, each set of layers does have their own, basically, their own legend. Now, I mentioned that the accuracy is an important factor here. So 79% was good, but was not enough. I mean, the ideal is 100%, but it's almost impossible to get 100% accuracy. So we take some more efforts by improving or tuning our algorithms, as well as collecting some more field samples from our partners, and with some tweak on our machine learning. So in the second, and provided a second generation map, which was published in 2020, just last year. And this map has some 7% higher accuracy than the previous map. Well, 7% may seem not really significant in many contexts, but here is a big deal. It is improving 1% of accuracy in the context of a country of 200,000 satellite image processing. 1% even is huge, but let alone the 7%. I mean, when it comes to reality, it means that the chance of a satellite that has detected correctly that this is bug is 80% now, than 79%. So you can multiply this number by the area of the country, and you can see that how many misclassification or error could lead that 7%. So that's we're still working on the third generation by using some more satellite data. As I said, satellite technology is a very evolving technology. Every year, every month, there are satellites that are being launched to the space and provide data sets to us. So we are taking benefit of them and then implementing in our algorithm to improve the result. But so far, the second generation have been published with 86% of accuracy. I think I just want to mention that this our map was the winner of Esri Canada 2020 map context. In other words, if you happen to have an Esri calendar on your wall in last year, then probably I think the month of January was this beautiful picture of wetlands of Canada. So that's a nice recognition of what we have done. And last year in American Geophysical Union, I was invited to present this work to AGU, to Google company, because we use their service. So they invited us, and I on behalf of the team, I presented some of these results to Google booth at AGU as well. Now, okay, we've done a lot for Canada. What's next step, or what are you doing for the US? As I mentioned, we are currently working on the wetland inventory of US. Now we are working on the wetlands inventory of Minnesota. Again, the status of wetlands inventory of US is much ahead of Canada, but still some of the maps are old and need revision, and in some areas there's not much detail in the old map, so we're trying to basically provide a seamless. Of course, this is a huge task and needs collaboration of many partners and industry. But I think over the past few months we built some good network of partners, from Fish and Wildlife Service to Ducks Unlimited, from academia, different people in academia, and so on. So we are we are improving our algorithm, and basically because it's not the way that the one we have built for Canada can be immediately used for the US. We have to tune, and we have to basically change the algorithms to work on the wetlands of the US. For example, one of the big differences is that the Canadian wetland inventory system is 5 major types of wetland that I mentioned, but in the US we have a wetlands inventory system which is called coordinate system, which is another different 5 type of wetlands that we need to consider, and this is an important basically input for our processing. So the ultimate goal right now, as I mentioned, we are working on the US site. So we're working right now on the Minnesota. Hopefully in the next few months we are done with the Minnesota, but of course, we can't get 100% of accuracy. The goal is to work and basically share the output and results with the partners, and be able to get feedbacks and back and forth to improve the result and implement their ideas as well. Then most likely we'll move to the state of Alaska, which is one of the, as I mentioned, to my knowledge, is one of the only states in the U.S. that doesn't have a full wetlands inventory. So that's why we want to move to that state, because for satellite data, there's no limitation, whether this is New York or Alaska. Satellite cover all of them. The fact that Alaska is a cloudy or a harsher environment than New York is true, but we are utilizing radar remote sensing as well. We're not relying only on optical remote sensing. So we can overcome that cloudy sky of Alaska. So the goal is, after US, we are moving, and we have started some initial negotiation and talk to Mexican partners. So the goal is to really include Mexico and at the end and provide a seamless wetlands inventory of North America in the next 3-4 years, I would say. So wetlands is one thing, and then be able to monitor it, because that is important. You don't want to map wetlands and just leave it alone. You want to be able to monitor the change of wetlands, to be able to study the climate change, and all anthropogenic factors that change wetlands. And even we would like to backcast how wetlands have been changed over the past 20 years, as long as there is satellite data. So these are the items that are in our to-do list as well. So we want to transfer from static mapping, so-called, which is one-time map of wetlands, to a dynamic mapping, which means that you're able to map wetlands on a yearly basis. Because again, satellite data is there, algorithm is there, processing power is there, so why not just put it the way that you be able to monitor? And this is a huge improvement for understanding our natural ecosystems and take more action toward climate change protection and all those. I want to take this opportunity to give a shout to all my project team. Like I said, Dr. Masood Matian-Peri and Dr. Fariba Mohammadi Manish, they were husband and wife, my 2 PhD students up in Canada. Did great job on this, still working with them. Dr. Brian Briscoe from Natural Resource Canada is a big player here as well, helping us with the consultation and with data sets and with some funding as well. And finally, my current PhD student here at ESF, Ms. Serena Adeli, who is working toward wetland inventory of the US. This is just a few names but we have a lot more people from this is people that directly work with me, but we have partners that I want to again give a big shout out to them, both from the Canadian side and from the US side. So Nature Conservancy Canada provided a lot of field data in Canada to us. Secor, the former company that I work with, and supported this project. Environment and Climate Change Canada, this is the big funder of this wetlands inventory map, so big thank you to them. Then Newfoundland and Labrador Government Research and Development Corporation of Newfoundland and Labrador provided funding to me a few years ago when I joined. And Natural Resources Canada, both funding, satellite image acquisition. We use some of these radar imagery that are not freely available, but they provided us for the research purposes from RadarSat. Then Ducks Unlimited Canada helped, contributed hugely. Then NSERC, Natural Science Engineering and Research Council of Canada, that basically fund one of my PhD students. And we use the free satellite data of the space agencies, or ESA, European Space Agency, through their Copernicus program. And last but not least, the Memorial University, which I was cross-appointed to them for a few years, and I'm still adjunct professor with them. And then moving to the US side, we are developing this network of collaboration, but again, big thanks to Ducks Unlimited, helping us with the ground truth data and field data. Then Minnesota Department of Natural Resources, again, big help and contribution to field data side and feedback to us, and also U.S. Fish and Wildlife Service through their National Wetlands Inventory System, and of course my beloved ESF. Thank you very much.
Dr. Salehi, thank you very much for that presentation. I really enjoyed it. I learned a lot, but I also have a lot of questions now. I know that you mentioned processing countrywide satellite data. How do you do that? I mean, there's so much data what processing methods are you using to get to that data?
That's a really great question. So when I talked earlier in one of the PowerPoints slides, is that we take the benefit of Google Earth Engine. So this is a cloud processing, which basically the processing, virtually the processing is happening with hundreds of computers that we don't see. So this is the beauty of cloud processing. We're not using the sole power of our desktop computer, but we're connecting through that cloud system. So many organizations offer cloud computations, such as Microsoft, such as Amazon, but Google Earth Engine is very interesting and neat in the context of our work, because they provide the access directly to the satellite data, basically the storage of satellite data and some processing functionality. So we take the benefit of Google Earth Engine. Without that, it probably takes forever to process on a single set of computers.
Okay. So now you have the satellite data, but now you have to get the field data in there as well. So how do you combine the two? And I know you mentioned something about 50,000 sets of data that you're doing from satellite alone. So how are you combining that with your field collected data?
Yeah, so probably most of us these days have heard about artificial intelligence, machine learning. So machine learning on its own is nothing. You have to train, you have to teach the software or the algorithm through some real world example. If you want to say, hey, go pick this satellite data and tell me where is fen, where is bug, it cannot. We have to show that. So this is, we should take some picture, real picture with our cell phone or with GPS. This is bug or fen, an example, and then go find the similar wetlands to this and label them as bug and fen. These are called so-called training samples. So we teach and training the algorithm based on field data, the real world data. So that's an important part. Some people think that remote sensing on its own can do anything, but really still the power of computer without interaction of human is very, very low. So we have these training samples, and like I mentioned, for a country like Canada or the US, collecting field, I cannot use the limited funding that I have, go to the field and try to pick all this, this is bug, this is fen, this is emergent wetlands. It takes time and it's very expensive. So we rely on our partnership. So for example, Ducks Unlimited has already collected lots of sample in Florida, in Minnesota, and in Texas, and we built basically a mutual collaboration that you guys provide us with this data set, then in return we provide the map to you. And then we built something together. So that's the way it worked, how it worked.
See, we still need people in there then. So I know that you also mentioned the fact that you're doing the monitoring for North America. I know you finished Canada, and that took, you said, if you put it all together, about 3 months. I know it probably took longer than that. But how long do you anticipate it taking for the United States?
Well, when it comes to the United States, we're still in the phase of developing the algorithm. So we're not finished with the algorithm itself, and it takes probably a year or two more. But we are not going, we are basically doing this sequentially. So we are testing and on smaller area, smaller area of Minnesota, then larger area of Minnesota, then the entire Minnesota, and then provide the data, the map, and then get connected with the stakeholder, and they get the feedback. So I would say, I guess, I am hoping by the end of the Serena's PhD program, maybe in 2 years, we should be at least have a sort of a preliminary map of the U.S. So.
Now, how often does that data have to be updated? So I know you said wetlands
Yeah,
are changing, so.
Once the algorithm itself is developed, then we have taken a huge burden of this work. Then the rest is just because satellite data is seamlessly are acquiring, and then they are available online. So we make simple code to get the data from the website and then be able to process them. That is a really neat thing, but it's not still, I guess, a ready product to be able to on time process these data sets. But after 2 years, once the algorithm is developed, we apply it to the entire US, and then we wait for another year to satellite data acquire more data, and then we apply it. So every year we can apply it, because wetlands is not type of thing that you want to monitor it every day. There's no change. So 1 year, according to our stakeholders and experts, is more than enough if you are able to monitor wetlands over a year. For some hot areas, some urban areas, urban sites, yes, you might be more frequently observe those, which needs higher resolution data sets. But talking about national scale, once a year is, I guess, is an ambitious goal, I guess.
Okay. Now, another question along those lines is, do natural disasters, fires, hurricanes, do they affect the wetlands, and would you monitor those areas a little bit more often?
I think I'm not the best person to answer that question, but the short answer is yes, of course. Fires, as it affect the forest, it does affect wetlands. Hurricane, obviously, yes, more impact. And flooding, I would say, is another important, basically, factor. And on top of all this, so these natural phenomena, have been there for millions of years, right? So nature go back to its origin, and it can rebuild. But the problem is the anthropogenic, or the factor that is human is the cause of them. So again, I'm not expert in that part, but yeah, wetlands are changed by any means.
And I know that when I was speaking about this to one of our alumni, they were very excited to hear about the 10-meter resolution of the satellite data. So can you explain that to me? Because I had no idea what that meant. So
No, that's a very valid question. So satellite data, that in the space there are thousands of satellites orbiting the Earth. So the type of satellite we use in remote sensing is those satellites with low orbit satellite, probably about 500 to 1,000 kilometers above the Earth. So the resolution of these satellite data are different, which means the minimum or the smallest object that they can see from space are different. Some satellites that are meant for to study the climate and hurricanes and oceans, the resolution are 3 kilometers, which is for study the climate and weather. You don't need to know 1 meter to see 1 meter, because you want to have the bigger context of the cloud and the movement. But on the other hand, some satellite data are designed and launched to the space are able to capture less than a meter objects. So you can count the cars. You can some satellites are able now. I'm not talking about the military satellite, but just the civilian satellite. They are able to basically detect even people and classify them. In this case, but those data sets are not freely available. They're very expensive. So you can't build a wetlands inventory product using those expensive 1 meter or half meter satellite data. Maybe in future, but there are a satellite data which is not 3 kilometers, not 1 meter, but about 10 to 30 meters, which is available. So that means we are using satellite data with the resolution, or each pixel size of the satellite is representing 10 meters on the ground, which means that you can, in a way, you can say that you can see any object equal or greater than 1 meter in size. And for wetlands, you're not looking for wetlands of 10 meters. That's not wetland. In minimum, so satellite resolution is one thing, then the minimum mapping unit is a different thing. So the satellite resolution data that we are using is 10 meter, but the minimum mapping unit sometimes is an acre, or in case of northern Canada, abandoned land, we go to 1 hectare.
So in the United States, do we have a lot of small wetlands?
Yes, we do.
Okay.
Yeah, we do. In fact, the regulation of coordinate classification system, they have different, we have to follow the rules and regulation of regulation that is, or the standard that's set by U.S. Fish and Wildlife Service. Sometimes even it goes to we have to pick up wetlands with a quarter of an acre even. So in some non-important wetlands, 1 hectare probably is fine, or 2 acres is fine. But some others, I know that, in fact, I attended a workshop. I presented some of these results to an ad hoc workshop with U.S. Fish and Wildlife Service with some expert in the field a couple of weeks ago, and we were discussing about this. Different areas, for in urban areas closer to the urban sites, you definitely need to have detailed maps than, say, in somewhere in Alaska. You don't care about whether wetland is 10 meter, or as long as you can map the large wetland, that is enough. So.
And then my last question to you is, I know we have all of our alumni that are out there, they're in the fields themselves. Do you ever use like citizen science data that they may be collecting on their own?
So that's a really, really good thing and good move. I have thought about it, but I haven't really used this citizen science. I know that there are some apps out there that allows that people can use their cell phone to measure trees and the height of trees. I think that would be a really great idea, and this is one of the things that I have thought for a while now. Really not toward implementing it, but I am thinking to put it in one of my proposals and suggested. I mean, somehow we use citizen science. Like I said, some of these field data they're not really field expert. As long as, if someone is taking some picture of their touristy sites over in Alaska, that would be extremely helpful for us. As long as the image has coordinates. So, and these days the cell phone, or you can set your cell phone to get the position or the location of the image. So it's a very, very helpful things. But we haven't used this in this project yet. No, unfortunately.
Maybe that'll be your next job.
Yeah,
you can
that's a
develop
good
that
idea.
app. There you go.
So I'll list you as my project partner in the proposal.
So I just wanted to say thank you very much for joining us today. It was a pleasure to have you. For everybody else that is joining us today, remember to subscribe to our ESF TV channel. That way you'll get announcements when we have new events coming up, or when we post new videos to our site. And I'm sure I just called it a video, and that wasn't supposed to be correct. But so I really appreciate everybody joining us today, and I look forward to seeing you next time. Take care.